Hello everybody, welcome back to another Engineering Statics lecture video. In this lecture video we're going to be covering the final topic of the lecture series, which is moment of inertia. Now since it's the final topic, that obviously means that the semester is coming to an end. So I just want to take this moment and say thank you all for the support on these videos. As you know, I'm not teaching the course this particular semester, so if you're watching these videos, it means that this is on your own time. So I apologize. I know you guys are probably getting a little bit sick of seeing my face every week, but that's okay because this is the last video and you won't have to see it anymore. Unless you take civil, then I'm going to pop up all the time, kind of like the boogeyman to always surprise you, if you will. With the semester also coming to an end, I just want to say I'm proud of you all. Coming to university for the first time, it's very difficult. I know it's a lot of students expect it to be just like high school, and as you've seen, it's not. You guys took your first midterm, got clapped pretty hard, as you guys will see, and I just want to say that that'll happen over and over again throughout your university careers. But the key thing is you just stick with it. Again, it was pretty depressing watching everyone get sad after the midterm, and you're all going to have bad midterms, you're all going to have bad final exams, but if you stick with it, you all go on to do great things. Again, I've had the pleasure of meeting many of you guys, and you are so much smarter than I am. So if I can do this, just imagine what you all can do. All right, I'm going to get emotional, so let's just go back to the actual theory, which is moments of inertia, and we can talk more about the semester at the end of the video. So moments of inertia. Moments of inertia is one of those really funny concepts where a lot of first-year students have been taught it by their instructor in statics, and then they come to me and say, Clayton, it's pretty easy to calculate, but what the hell does it mean? Well, basically, moments of inertia is going to be a measure of how easily a body bends. Now you're saying, what? Because if we look, up until this point in the entire course, we've only discussed rigid bodies, which are bodies that do not deform. And we're saying, okay, that's great, but now, spoiler alert, you're all the masters of rigid body. Everything that has to do with rigid bodies, you've conquered. Now it's time for you all to take the next step, which are bodies that actually do deform. So that's why I said this video is kind of the gate to actual engineering, because you took a very simplified assumption, which is rigid bodies, and now we are going to start talking about bodies that actually deform. It's going to it sounds like it's going to be very complicated, but it's actually not. Let's say that we have a simply supported beam with a load Q. Again, you are now the masters of rigid bodies, so you can find out the support reactions, you can find the shear diagram, you can find the bending moment diagram. So it's only logical that the next step we would take would be actually finding the deflection of this beam. Now, if we were to look at a simply supported beam, let's say a ruler, and it had some load, we know it's going to start arcing and kind of make a smiley face. So we know that the deflection of the beam is going to be something like this. Now, it turns out for linear elastic materials, we can actually measure the deflection at certain points. For instance, if I wanted the deflection, which I'm going to call delta, at the midspan, I can actually calculate it using the following formula, where it's 5 times Q times L to the 4. So Q is our distributed load. You all know what that is. L, that's going to be the length of the beam. Again, you all know what that is. And then it's divided by 384 EI. So if we were to look at this formula right here, you guys know everything in it besides two things, and that is going to be that EI term. So as we see, the bending of beams is a function of E as well as I. E is what is actually referred to as the Young's modulus, and it's related to the material that we use. It makes sense. If I were to take my ruler and bend it, well, I can only bend it this much because it's made out of cheap plastic. If I were to take something much stiffer, like my iPad, which is made of metal, I can't exactly bend it. Well, at least I don't want to try to bend it, or else we would be having a very bad time. So basically, this is related to the material properties of a beam. Makes sense. If we have a stronger material, it's not going to bend as easy. For example, for steel, this would be 200,000 MPa. So as we're going to see, it's typically constant in these elastic materials. The second one, which is kind of the topic of today, is moment of inertia, and it's related to the geometry of the cross-section. As we're going to see, depending on the cross-section of our beam, it's going to bend either easier or harder. The best example would be if I were to take a book and I were to bend it this way, as we can see, it's very easy to bend. But if I were to flip it over, so again, I didn't change the material properties, I didn't change the length or anything else, and I were to try and bend it now, well, as we can see, it's not really bending. Easy to bend one way, not so easy to bend the other way. So bending of beams is related to two things: material properties as well as the geometry of the cross section. And that geometry of the cross section is going to be the topic for today. So if we were to do a simple example of which one's easier to bend, and I were to have two rectangles, a purple one and a blue one, and again they have the same dimensions, same length, same material properties, we already know that that blue one is going to be harder to bend. We just did the example. So this would be the purple one, nice and easy. This would be the blue one, very hard. So again, intuitively, we know that the blue shape is going to be harder to bend. And the reason why is because it's actually going to have a larger moment of inertia. If we were to compare the two, we can see that the blue one is around 4 times as much as the purple one. So we can see that the math actually checks out. Intuitively, we know it checks out, but how exactly do we calculate this moment of inertia? Well, it's actually pretty simple. The moment of inertia, which again, which it can also be referred to as the second moment of inertia, is basically a measure of how efficient a cross-section is at resisting bending. Now, the formulas for them are actually quite simple. If I want the moment of inertia about the x-axis, it's going to be the integral of y squiggle squared dA. And if I want the moment of inertia about the y-axis, it's going to be the integral of x squiggle squared dA, where x squiggle and y squiggle are the distance from the axis to the centroid of the element, and dA is going to be the area of the element. So this is going to lead to the first key thing I want you all to remember about moment of inertia. If we look at y squiggle and x squiggle, it's the distance from the axis to the centroid of the element. So depending on where our axis is, the moment of inertia is actually going to change. So again, the moment of inertia is dependent on the location of our bending axis or our rotation axis. So if we were to have a scenario here where I were to have two identical beams or beam cross sections, and one of them was slightly farther away from the axis, or the x-axis in this case, that would be the blue shape, and we were to look at y squiggle, well, we can see for the purple one it'd be around this distance, but for the blue one it's going to be much greater. And if we look at our formula for moments of inertia about the x-axis, as we can see, we're going to take that value, that distance, and we're going to square it. So this would actually result in the blue shape having a much greater moment of inertia than the purple shape, even though they are the exact same shape. Now you're saying, Clayton, this is amazing. How can we actually do this or take advantage of this in design? Well, you see it all the time. This is why you see I-beams, or they're actually called W-shaped beams. We take a lot of that area that's in these shapes and we try to push it to the farther ends, because typically in design we want the moment of inertia about the centroid. So if we were to look at this shape, we know it's symmetric. So the axis that we'd want to take the moment of inertia about, it's around the center, and we want to take a lot of that area of the shape and push it as far away from the center as possible. So this is why you see beams like this. They also have other advantages in terms of strength, but we're not going to actually talk about that. You'll see for a lot of the very long span beams where we'd have a lot of deflection, this is why we use beams with such a great depth. So these beams right here, these would be something like bridge girders where they have to span maybe 30, 40 meters. So if that's the case, again, we want our shape to have a high moment of inertia so that when the cars don't go by, the beam doesn't just sag like this. That would be pretty scary. So now that we have the formula and we know what moment of inertia is, we can start calculating the moment of inertia for some simple shapes. So let's start off with a rectangle. Again, as I said, typically in design, we're mainly interested in the moment of inertia about the centroidal axis. So this would be the axis that passes through the centroid of our shape. Because as we'll see later on in design, or I guess I'll see, you may not see, this is about where our shape would bend. So if we were to actually look at our rectangular cross section here, you'd find that if this is truly linear elastic, all the area above the x-axis would be in compression, and all the area below the x-axis would be in tension. That's why we're so concerned with things about the centroid. So if we were to take our shape and we wanted to find the moment of inertia about this x-axis, well, we know that our formula is simply going to be the integral of y squiggle squared dA. So again, the whole process here is going to be the same for centroids, where in order to solve this integral, we want to basically take a slice. So what we're going to do is say, okay, do I take a vertical slice or do I want a horizontal slice? Well, you can take either or. They're going to give you the same answer. But for me, I always look at what I have in here. So right here, I have a y squiggle. This basically means to me that I want to have my integral in terms of dy. I want a dy in my integral. It'll make my life easier. So in order to get a dy, I need a horizontal slice. So I'm going to take a horizontal slice here, and we know that y squiggle in this case is just going to be equal to y. Now if I were to actually take that slice and kind of expand it, we already said that the height of this slice is going to be dy. Again, that's why I picked the horizontal slice. And we know that the width of this slice is going to be b. If we were to look at our entire rectangle, it doesn't matter where this slice is, it's always going to have a width b. Now this is nice because dA, which is going to be the area of the slice, is simply just going to be b times dy. So I can substitute that into my integral over here to get b times y squared and integrate that with respect to dy, which gives me this nice load of crap here. And then we figure out that the moment of inertia about the x-axis is going to be equal to base times height cubed divided by 12. I guarantee you by the end of your engineering careers, you will have this memorized. Everyone does. Now for the y-axis, it's going to be the exact same thing. The only thing is I'm going to look at this and say, okay, since I have an x squiggle, I want a dx. And a dx actually corresponds to a vertical slice. So I'm going to take this green vertical slice, and we'll get the following relationship for the area. And if I were to do the integral, I'm going to get height times base cubed divided by 12. Now this starts to explain why if we take a shape and we were to orientate it this way, it bends a lot easier than if we were to take a shape and bend it this way. Look at the terms here. We have a height cubed. So if the height is much greater, well, it's going to go almost exponentially up compared to the base, and that's going to make a big difference. So we can conclude that the moment of inertia for a rectangle about the centroidal axis is just going to be base times height cubed divided by 12 for the x-axis, and height times base cubed divided by 12 for the y-axis. As we can see, this is a piece of cake. You're all laughing. Now here comes the first trick, and that is parallel axis theorem. Now whenever you see theorem, you have bad flashbacks to math, but this one's actually pretty simple. Parallel axis theorem says, okay, if we know the moment of inertia about the centroidal axis, we can actually very quickly determine the moment of inertia about a different axis. Remember we said in our formulas here that the moment of inertia, the actual value that we calculate, is dependent on where that axis is. So if we have a rectangle, again, we found Ix as base times height cubed divided by 12, but this is only if our x-axis passes through the centroid of our rectangle. And you're saying, okay, well, what exactly does this mean? Well, it means that if the prof wants to be mean on the exam, they're going to say, okay, you know it about the x-axis that passes through the centroid, but what happens if I want the moment of inertia about this axis x prime? Now, if you don't know parallel axis theorem, you're going to have to go integrate. No one wants to integrate, let's be honest. And as we can see, there's a slight typo in this formula. It should be y squiggle squared. But if I wanted to, I could easily find the moment of inertia through the integration method. I can take a horizontal slice, I can do my integral, and I can get that it's actually base times height cubed divided by 3. So again, notice that depending on where the axis is, the moment of inertia is actually going to change. This one, as we can see, if I were to take my axis as the bottom of the shape, my moment of inertia increases because, again, I have a lot more area farther away from my axis, if that makes sense. But this is the trick. This is the goal of parallel axis theorem. You're saying, Clayton, I don't want to integrate. Integrating sucks. Well, parallel axis theorem basically says that if we know the moment of inertia about the centroidal axis, which we do, base times height cubed divided by 12, then we can easily determine the moment of inertia about any parallel axis. Well, you're saying, okay, how do we do that? Well, it's simple. The formula is the moment of inertia about any parallel axis is going to be equal to the moment of inertia of the centroidal axis plus a times d squared. Now you're saying, okay, well, what is a, what is d? Well, a is the area of our shape. So if we look here, if we have a rectangle, it's base times height. And d is actually going to be the distance between the two axes. So if we were to apply this to the example above using parallel axis theorem, we can say, okay, the moment of inertia about x prime, again the one that we want, is going to be the moment of inertia about the centroidal axis, which we have right above, base times height cubed divided by 12, plus a times d squared. Well, we already said that a is going to be base times height. Again, it's just the area of the rectangle. And this d is going to be the distance between the two axes. So if the centroid is located at h over 2, we know that d is going to be h over 2. So if we were to substitute all this in, we actually arrive at the exact same answer, base times height cubed divided by 3. But the key thing here is we didn't need any sort of integration. How sexy is that? So this is why parallel axis theorem is so nice. Now between us, this is what typically happens on exam type scenarios. Typically, I don't want to say typically because I know for the U of A this is true, but I don't know wherever else you're from. We as instructors will give students the moment of inertia about the centroid of simple shapes. So a square, a rectangle, triangle, a circle. And then what we'll typically do is we'll ask for the moment of inertia about a different axis. Now the thing is, if students don't know about parallel axis theorem, it's going to suck. It's going to suck a lot. But now if we look at parallel axis theorem, if we know the area and distance between those two axes, and we're given the moment of inertia about the centroidal axes, it actually makes calculations a lot easier. We are going to do an example of this later on in the lecture video. But some of you students, I know there's some of you, like Shirley, that's going to say, hey, how exactly is this true? Can you show a proof? Well, of course I can show a proof. We can actually prove parallel axis theorem by considering a simple scenario. And that is this. Let's say that we have a random shape, and this was about as random as I can get in PowerPoint. Kind of looks like a deformed Pac-Man or something like that. And let's say that it has a centroidal axis, x prime, and we want the moment of inertia about a parallel axis, x. Well, we know, for instance, that the formula for the moment of inertia is going to be the integral of y squiggle squared dA. I can't believe I forgot the squared twice. I'll fix that and put those into the lecture notes. So if we were to look at this, and we know that y squiggle is basically the distance from the axis we want, in this case the purple axis, to our element, we know that we can expand this to d plus y prime squared dA. From there, since I have something squared, I'm going to expand it as follows. So we have y prime squared plus d squared plus 2 times dy. And then from there, I'm going to separate it basically into 3 integrals, which I'm going to call 1, 2, and 3. Now, if we were to look at these integrals, the first one's pretty simple. It's the integral of y prime squared with respect to dA. So basically, the distance from our centroidal axis to our element squared dA. Well, hold on one second. This is just the moment of inertia about the centroidal axis. So this would be the moment of inertia with respect to x prime, the red axis. If we were to look at the second one, we have the integral of d squared times dA. And remember that d, the distance from our axes, well, that's just a constant. So I can actually factor that outside of the integral, where I get d squared times the integral of dA. And we know that the integral of dA is simply just going to be area. So that one's also not too bad. The one that starts to trick students up if they're ever trying to do this proof is this third one, where we have the integral of 2d y prime dA. Remember, d is constant, we can take that out, but y prime is not constant. So that's something that we have to be aware of. So we can simplify our integral into 2d times the integral of y prime dA. And if you remember back from centroids, this is essentially saying 2d times the moment about the centroid. Now, it's not exactly equal to moment, but this is going to be the best way I can explain this to you. If we were to look at our centroidal axis, we know that at this point everything should balance. Now, of course, I'm not going to be able to make this balance. This will be a bad time, but you get what I'm saying. It's going to balance, meaning that all the moments on the left side are going to cancel with the moments on the right side. So because of this term, this is actually going to be equal to 0, because the concept that is at the centroid, everything actually balances. All right, I feel like that Thanos meme is going to come up, but you know what I'm saying. Everything balances. So the summation here should actually be equal to 0. And if this is the case, well, we know that the moment of inertia about the x-axis is going to be equal to the moment of inertia about the centroidal axis plus a times d squared. Now this is very important. I want you all to remember this. This term right here will always be the moment of inertia of the centroidal axis. And the reason why is this. If we were to look at that third term there, that integral, where we said because it balances, it's equal to 0. Well, if we were to take the moment of inertia at some other spot, we're going to have a scenario where it doesn't balance. So that third part right there would actually be non-zero. So it's something to be aware of. This formula only works because we're taking the moment of inertia about the centroidal axis. Now you're saying, Clayton, what can I do with parallel axis theorem? Well, there's going to be a bunch of things. The first one is it actually allows us to solve for the moment of inertia for other simple shapes that we normally couldn't really do using the integration method. The best example would be a right triangle. If I were to look at the centroidal axis, which we have displayed here, and we say, okay, if I want the moment of inertia about the x-axis, it's going to require a horizontal slice, just like before. Well, you can immediately run into problems because it's very difficult to define the actual base of this slice. It becomes quite difficult. It's not impossible, of course, as you math nerds know, but it does become very difficult. So rather than actually going from the integration method directly into the centroidal axis, let's consider a different scenario where I want to calculate the moment of inertia about this axis right here. Again, this one's not the centroidal axis, but in this configuration, our life is actually a lot easier because I can define my horizontal slice as follows and say, okay, if my horizontal slice is here, then we know that y squiggle is just going to be equal to y. And if I were to look at the slice itself, we know that it's going to have a thickness dy, and it's going to have the base as a function of y, which is going to be b minus b over h. I don't know why I can't say that, times y. Now, the first thing I'm going to get mentioned a lot is, hey, Clayton, how exactly did you get that? Well, keep in mind that triangles are just linear lines. So all I did was take y equals mx plus b, and then I rearranged for x. So it's not too bad. Now that I know both the base and the height of this slice, I can find the area as simply base times height. And then from there, I can go into my moment of inertia formula. I got it right this time, which is nice. Where it's the integral of y squiggle squared dA. I know what dA is, as well as y squiggle, so I can substitute everything in. And I get base times height cubed divided by 12. It's actually the same as a rectangle, believe it or not, for this particular case. Now, this is nice because I can take what I've learned on the parallel axis side, and now I can come back to my centroidal axis side and actually calculate the moment of inertia about the centroidal axis. If we look at parallel axis theorem, we know that Ix is equal to I bar x plus a times d squared. Again, I want to find the moment of inertia about my centroidal axis, which is going to be this term right here. So in order to do that, I'm going to rearrange the formula where Ix bar is equal to Ix minus a times d squared. And if we were to look at this, we actually know what everything is. The first one is we need the moment of inertia about any axis. Well, if we look on the right-hand side, we found the moment of inertia about the axis that is parallel to the base of the triangle. We have that as base times height cubed divided by 12. We need to know the area of the shape next, but that's just going to be 1/2 base times height. And then the last thing we need to know is d, the distance between the two axes. And we know that for a triangle, the distance between the base and the centroid is going to be h over 3. So everything is lining up quite nicely. We can substitute everything into this formula, and we get base times height cubed divided by 36. And if we were to repeat this same process for the y-axis, we can conclude that the moment of inertia for our right triangle is going to be base times height cubed divided by 36 for the x-axis, or height times base cubed divided by 36 for the y-axis. So it's pretty nice. But again, I told you, in exams, typically they give you the moment of inertia for all these simple shapes. And you're saying, okay, well, if they just give it to us, what's the challenge? Well, just like centroids, many exam questions focus on the moment of inertia of composite bodies. So these are bodies where it's basically an assembly of simple shapes connected together. So if we were to calculate the moments of inertia of one of these composite shapes, all we need to do is find the centroid of the composite shape, and then using parallel axis theorem, find the moments of inertia of each of the simple shapes around that centroidal axis, and then sum it all together. Now I know you're reading that thinking, what? Like, come on, Clayton, that's a bunch of word garbage. Show me what it means. Well, let's go back to this example over here. This is something that we actually covered in centroids. Let's say that I wanted to know the moment of inertia about this composite shape about its own centroidal axis. So if we were to look at this shape, we know from the centroid lecture video, we can figure out the centroid of each of the two shapes, y squiggle b and y squiggle p, and we know that the composite shape has a centroid y bar. So typically in exam scenarios, you will see that moment of inertia and centroids, they're actually covered in the same question, because for many cases we need the centroid to find the moment of inertia. If we didn't know what y bar is here, well, then we actually can't find the moment of inertia because we're going to need those distances. Now, we actually covered this exact example in the centroid unit, and we figured out that y squiggle b is 50, y squiggle p is 115, and y bar is around 81. I believe it was 80.8, and I know that some troll in the comments is going to mention that, but we're just trying to keep it simple, so I just left it as 81. So again, the whole goal here is to find the moment of inertia of this composite shape around the centroidal axis of this composite shape, which is going to be that red dashed line. This is why knowing the moment of inertia of simple shapes is going to come in handy. If we were to look at our purple shape at the top, we know the moment of inertia for a rectangle is base times height cubed divided by 12. Now the problem with that is that will give us the moment of inertia about its own centroidal axis. That'll be the purple dashed line. So if I were to calculate the moment of inertia about this centroidal axis, base times height cubed divided by 12, I get a number, but again, that's the moment of inertia around the purple line. To convert it to the moment of inertia around the red line, we use parallel axis theorem. And the only thing I actually need to know is the distances between those two axes, which I call dp, which I know a lot of you are probably chuckling. I am too, but I probably shouldn't talk about stuff like that with this greasy mustache, so I'm just going to leave that be. So if we know what the distance between these two axes are, we can actually find the moment of inertia of our purple shape around the red axes. All we need is the moment of inertia about the centroidal axes, which we have, the area of our shape, you guys can figure that out pretty simply, times the distances between, or the distance between that axis squared. So we have everything we need. We can find out that. And we can repeat this process actually with the blue shape. So we know that the blue shape is also just a rectangle. So we can find its moment of inertia around its own centroidal axis, which is going to be that blue axis there. Calculate that using base times height cubed divided by 12. And then again, I want to convert that moment of inertia to the moment of inertia around the red axes. Again, using parallel axis theorem, I can find the distance between those two axes, and I can calculate it as follows. From there, I can find the total moment of inertia of this composite shape just by summing everything together. So all I'm going to do is take the moment of inertia of the purple shape around the red axis and add it to the moment of inertia of the blue shape also around that red axis, and we get the following. So as we're going to see, it's very similar to centroids, where you basically treat each shape independently and then add it together at the end. Now, one thing too that I won't show here through an example, but it's fairly easy to know, is we can also have holes. And if that's the case, all we need to do is find the moment of inertia about the hole and then subtract it from our total moment of inertia. Again, it's the same thing that we did in centroids. If we have a hole, we just treat it as a negative area, if you will. So that's going to be moment of inertia. Now, there's going to be two other kind of different topics that we're going to talk about. And the first is the radius of gyration. The good news for students is that if you know the moment of inertia, radius of gyration is a piece of cake. So basically, the radius of gyration is a measure of the distribution of cross-sectional area from the centroidal axes. Now you're saying, what? Well, the best way to describe it is to show you guys kind of an example. Let's say that we had a rectangle, and we said that if we wanted to find the moment of inertia about the centroidal axis in the x direction, it was just base times height cubed divided by 12. Now we're going to take this and we are going to express it in an equivalent system. So rather than having an actual rectangle, I'm going to take it and just express it as a point. Now this point right here is the entire cross-sectional area of the shape on the left kind of concentrated in a single point. And here's the trick. What I want is I want both of these scenarios to have the same moment of inertia. So we know that in order to get this point to have the same moment of inertia as the shape on the left, we're going to have to specify a distance. And this distance right here, well, that's actually the radius of gyration. So that's all it is. Now, if you want to calculate it, again, it's pretty simple. It's just going to be the square root of moment of inertia divided by the area. So if you found moments of inertia, well, chances are you know area at that point. All you need to do is divide one another and then square root it. So it's a piece of cake. Now you're saying, okay, Clayton, how the hell do you use that in design? Well, radius of gyration actually makes our lives a lot simpler, because what it's actually related to is instability problems known as buckling. Now, buckling is something that you've probably already seen a lot before. If I were to take something very slender and I were to squeeze it, as we can see, there comes a certain load where it just pops out to the side. That's known as buckling or instability. Now, we can actually calculate this force using the following formula, where it's pi squared EI divided by basically the length or the height of our object squared. This is known as the Euler buckling load. Now, if I want to express this load in terms of stress, we know that stress is simply going to be force divided by area. So if I were to divide it by area, I get the following term. Now, if we look in here, we actually see something special. We have an I at the top and we have an A at the bottom. Moment of inertia divided by area. If we look up at our radius of gyration formula, well, we basically have the exact same thing. So I can substitute the radius of gyration into this formula, and then if I were to rearrange it, I get the following, where I get pi squared E, where again E was related to the material properties, divided by this term right here, where it's basically the height of our object divided by radius of gyration. This is actually called our slenderness ratio. If you look at concrete, steel, masonry, timber, all of them have specific rules regarding slenderness ratios. Because what happens is the higher the slenderness ratio of your structure is, the chances are it's going to buckle. You don't want things to buckle. It provides no warning and it's basically just a collapse. So a lot of the codes will say, okay, if you have a high slenderness ratio, which again is based on radius of gyration, you have to do a lot of very specific things when you design. One of the things that we talked about earlier, I'm not too sure which lecture, was the idea of second order effects. We said that if we were to have a wall or something that had basically a lateral load as well as an axial load, we don't actually have any moment produced by that point load P. But we said if we consider deformation and the wall starts to bend, well, now that point load P is actually going to create a moment about O. So what you'll see is a lot of clauses in steel and especially concrete and masonry. They say if you have a slenderness ratio and it's typically greater than 30, so if you have a slenderness ratio greater than 30, you're going to have to start worrying about all these problems. And you're going to have to do extra analysis, and it actually becomes pretty gross. It makes design pretty hard. But the key thing I'm trying to say is moment of inertia plays a key role in actual design. The last one is polar moment of inertia. Now, I'm always honest with students. You'll never really see this. Moment of inertia, as we talked about, is how easily something bends. So as we can see, we said in different directions, it bends a little bit different. What polar moment of inertia is how easily something twists. Now, twisting is something that you don't want in design. It's actually referred to as torsion. You don't want torsion in design because the code books don't really have any clauses against it. The steel code in Canada, for instance, basically says if you have torsion, just make sure it's safe. They don't really provide any rules or regulations to guide you to make sure it's safe. It's one of those very complex problems. So as engineers, we typically design our structures to avoid any sort of twisting. Now, if you want to figure out the polar moment of inertia, it's actually going to be the integral of r squared dA, where r is actually the radius. So this formula right here is actually in polar coordinates. Now, if we want to, you guys are saying, Clayton, I've taken math. I'm not dealing with polar coordinates. Get that shit out of here. I don't want to deal with it. Well, we can also express it in rectangular coordinates because we know that the radius squared is equal to x squared plus y squared. It's basically just a triangle. And if this is the case, we can actually substitute this into our formula above. And we basically have two different integrals. The first one is x squiggle squared dA, which is the moments of inertia about the y-axis. And then the second one is y squiggle squared dA, which is the moments of inertia about the x-axis. So if you want to, you can just add them together to find the polar moment of inertia. But the reason why we have to typically keep it in polar coordinates is a lot of the objects that we consider for twisting action are actually circles. So if we had a circle here with a radius r, we can actually find its polar moment of inertia using the formula above. Now it's going to follow basically the same steps as before, where the first one is we need to take that dA term and express it in terms of something else. So if I were to look at my shape here, what I can do is I can take a nice little slice around, and we're going to say that this slice is located at a distance r. Now if I want the thickness, or sorry, the area of my circular slice, it's going to be the circumference times the thickness. So 2 pi r, again, the circumference, times the thickness, which we know is dr. We want that thickness to be basically minuscule. From there, we can substitute everything into our formula here, and we know that we have the integral from 0 to r, the radius, of r squared times 2 pi r with respect to dr, and then we get pi over 4 r to the 4. So this is how you can find the polar moment of inertia, but again, I've never actually seen it used, so I want to make that clear. The only time I've actually ever used this in design was the torsion of steel structures, but that is so rare that you basically never ever see it. Moment of inertia, though, the original one, you see that all the time. Radius of gyration, again, you see all the time. This one, not so much. But yeah, that's it. And as I said before, that's it for this course. So I want to thank each and every one of you for sticking around, watching my videos, all the support. I really appreciate it. The whole goal of these videos was to basically make your lives as easy as possible. Again, first year engineering, it can suck, it can blow chunks, but you did it. If you're watching this video, it means that you're at the end, so congratulations, you did it. And again, I just want to thank all of you. It's been such an incredible semester. I've got to meet a lot of you guys. Shirley, the genius, Raph, who's the loudest person I think I've ever met in my life, and so many more. So thank you all so much. I really appreciate it. If this is our last interaction together, I just want to say best of luck in your careers. I'll be rooting for you. If you're in civil, well, again, I'll pop up every now and again. So again, thank you all so much. I really appreciate it. That's it for this lecture video. So I will see you civil engineers in your next course.